Okay, good afternoon, everyone. So we'll start in just a few minutes. Okay. Hi, good afternoon, everyone. How are we all doing today?
Good and you?
Not so bad. Um, so basically, the stuff we're doing now is based on electromagnetic waves, specifically light spectrum, visible light, but the stuff we are seeing in chapters 34, 35, and 36 is stuff that works for all wavelengths of EM radiation. It's just that when considering visible light, it makes it so that all the stuff, all the apparatus and effects like diffraction, dispersion of light and so on, it makes those effects visible to the eyes. It's very easy to picture what's physically going on when we talk about anything from prisms to mirrors to telescopes. What else was I going to say? Don't want to do anything too hard this tutorial since I know we're just wrapping up midterm week. So most of the questions today will be sort of simple mirror and lens equations, nothing too hard. Lenses can get tricky, but there is the what's called a thin lens approximation that basically assumes that the lens is fairly thin, and that lets you use a formula for figuring out the image produced by any lens. That's a lot less complicated compared to a thicker prism. Anyhow, the tutorial slides are up in Omnivox, so put up the remainder of the lectures for chapter 30. I get confused because the textbook cuts off one chapter in the new picture in the new edition, but it should be chapter 35, I think, that we're supposed to be working on. So I think, yeah, if you have the latest edition, this is probably chapter. In the newest edition, it's chapter 35 that we are on, and in the edition that I have is chapter 36. Anyways, reflection and refraction in my book were chapter 34, so I guess now it must be chapter 35. Either way, we're supposed to be doing the reflection and refraction chapters last week, and now starting today, I'll start putting up the lectures for the lenses and mirror chapter. But last time when I did a tutorial for reflection and refraction, one thing I didn't get to do problems for was the case of total internal reflection, which is simply when light doesn't transfer out of the medium it's in. Light just keeps getting reflected, stays in the medium, right? And the reason this happens is because light tends to want to move away from the normal if it goes to a faster medium. So we have the drawing here on the left, you see light shooting from a thicker and more dense medium. The rays are coming out from the bottom left, and they each strike the normal at a bigger incidence angle if you look at the rays from 1 to 5. So 1's perfectly parallel to the normal, and 2, 3, 4, and 5 are bent farther away. So when they strike the surface, they're passing on to a faster medium, and that will make light move away from the normal. But eventually, though, you reach such a big angle of refraction that what you visibly see is that no light is transferred, light just kind of vanishes. And the reason that is because at this point, to reach a critical angle, where light will technically be refracting at 90 degrees, and anything past that, if you were to shoot a ray that's deeper than ray 5 in drawing A, or even, let's say 5 is probably hitting the surface at an angle of like 60 degrees. If you were to hit a ray that hits it with 70, 80 degrees or above, then the ray would just get reflected back entirely. Rays 1, 2, 3, and 4, rays 1, 2, and 3, right? They transfer through, and in the case of 2 and 3, part of the energy goes through and part of the energy gets reflected back. So with ray 1, actually, you can't see it, you can't really see it, but even though ray 1 shoots straight up, so there's no refraction, some of the energy does bounce back down. But ray 4 is at the critical angle, so all of the energy in ray 4 just bounces back into the medium. And ray 5 is past the critical angle, it's bigger than that, so it also remains inside, and so will any ray that's deeper than ray 4. And we derive the formula for the critical angle using Snell's law, where Snell's law lets you predict the refraction angle if you know the incidence angle and the indices of refraction of the mediums. So if you have information about how light moves in each medium and you know what the incidence angle is, you can find how light will refract. And we said this critical angle is the incidence angle at which light refracts by 90 degrees from the normal. And then you manipulate Snell's law to say, okay, there's some theta that makes the refracted angle 90 degrees. So you end up deriving the formula for this theta, this critical angle, in terms of that, which is shown here. And because this only happens when light bends away from the normal, you can only have this total internal reflection happening when you move from a slow medium to a faster one. So I have a few questions to show this. Diver is underwater, and they got this, one of those underwater searchlights that works well underwater. That's why they're called underwater searchlights, self-explanatory. And at one angle, they have to shine it to reflect internally. So it's kind of cool, actually, that if you're taking pictures from underwater, right above you, light, comes at a narrow cone, so it's within the critical angle. But outside of a kind of like surface window above you, where you can see the sky above you, outside of that cone where you can see stuff, the light surrounding that cone above you is actually totally reflected back, so you can't see over the surface of the water. Something called Snell's window, which actually, oops, like that. Kind of see, you can kind of see it here. I have no idea where the heck that took me. So you can kind of see a picture here. You see how like you can see the water looking transparent in the top part here. The blue sky can be seen above, but outside that area, you see that you only see darkness. You only see light being trapped in the water. Here you see it. If you take the camera, you kind of shoot the picture right above you. You see that the window that lets you see outside is pretty much a circle, because right, it's kind of like you're projecting a cone above your head, where everything within that cone falls within the critical angle, which lets light pass through the water, making it transparent when everything surrounding that looks dark because light can't pass. Anyways. So we know that we're in the water, so we know that total internal reflection can happen. The critical angle formula is always the same, so this type of question isn't necessarily too complicated. Critical angle is usually pretty big for stuff like liquids. So if we know then that so the question asks at what angle will light be totally reflected? So like we said, it's a range of angles. Anything bigger than the critical angle will ensure total reflection, but we then just calculate the critical angle as the basis of that. So the formula is always the same, right? It's just the sine of the critical angle is equal to the ratio of the second medium's index to the first. So in this case, remember that the N2 represents the outgoing medium, or wherever the light would like to refract if it could, but in this case, it's reflecting internally. So in this case, N2 means the air, and N1 is the water where the diver is. And the idea is that the angle of incidence is so big that all the light just kind of bounces back. So turns out then that the actual angle, to get the angle, well, just use inverse sine, arc sine. N2 is air, which is approximately 1, water is 1.33. And if you plug that in, you should get an angle of around, I want to say like 70, 75, 76 degrees. It's also worth pointing out that if you look at the ratio, right, you have a fast medium over a slower medium, right? N2 over N1. So for light coming from inside solids that generally have a bigger index of refraction, the critical angle is going to be smaller. So light has to be bent at 76 degrees from the surface of water to get reflected. But for something like a diamond, the critical angle is a lot smaller, which is why they're so shiny, because most of the light in diamond just keeps reflecting off inside, and only so much of it comes out back at you. So they sparkle since a lot of the light just gets reflected around and then back to your face. Okay, so this example, we've changed the surfaces a little bit. We now have ethyl alcohol and we have water on top. So if you ever try to mix the water and oil in the same glass, right, you see that one of them sits at the bottom and one sits on top. Or if you ever just pour honey into your tea, you see that the honey just sinks to the bottom and you gotta stir it. Or if you pour coffee on top of your milk and you do it slowly, the milk sits at the bottom, you gotta stir it in. So that's kind of what happens with liquids, that the denser liquid will just sit below the less dense ones and they'll kind of remain stacked together unless stirred. So you can have a flask of ethyl alcohol, in this case being a top of water, and water is in this case actually denser than the alcohol, despite having a lower index of refraction. But it's gonna put this question, it's kind of like describing, it's just some beaker here that contains both the water and the ethyl alcohol. So okay, so in this case, the question's asking, okay, what angle the interface of the two liquids is light totally reflected? So if light is coming in from the alcohol towards the water, the light that passes onto the water will refract away from the normal, but light coming from the water into the alcohol will refract towards normal. So if I were to draw a light ray that's emerging from the water, kind of like say from here, you can kind of picture the normal line here. The light from the alcohol, the light coming in from the water into the alcohol will get refracted because water has a lower index of refraction and alcohol has a bigger one. It'll get refracted out towards normal. And actually above the alcohol, the light ray reaches air. So in air, it will refract away from normal. But just between the water and the alcohol, from water to alcohol, light bends towards the normal. In the case of light coming in from the alcohol, though, light will bend away from the normal. So let me just draw the normal line again. And then in this case, the light will be further away from the normal. So you can only have total internal reflection within the alcohol. And the approach in this case is, again, the same one for the diver in the water, but now it's different indices of refraction. So and again, the N2 is the medium you'd like to refract to, but you can't in the case of internal reflection. So it would be that of water in this case, and the bottom one would be that of the alcohol. So then theta C is equal to arcsine of the water 1.33 divided by 1.361. And
Sure.
yeah.
How are we supposed to know that the H2O is supposed to go above the alcohol in the formula?
In this case, we're just told that the alcohol sits on top of water. The question tells you.
Okay, thank you.
Yeah, no worries. This isn't chemistry class, so you won't be expected to like memorize the densities of everything. Yeah, less memorizing numbers in this class. Anyways, I'm pulling out my calculator for this because I can't do mental math when it comes to arcsine. It's like it's you can kind of eyeball it, but a number of 1.33 to 1.36, that's really close to 1. So with the angle, should probably be really close to 90 degrees. Yeah, it's 77. So the reason why I said that the angle should be close to 90 degrees is because, right, the sine function goes from 0 to 1 as theta goes from 0 to 90. So 1.3 over 1.36 is close to 1. It's closer to 1 than 0. So we expect then that theta should also be closer to 90 than to 0 degrees. That's my way of eyeballing arcsine, but I mean, you should be using a calculator anyways.
Sir?
Yes.
So like the light is being sent from the water to the alcohol, or the light is being sent from the alcohol to the water?
So in this case, the light, only light beams being sent from the alcohol towards the water can get total internal reflection. So only light rays that are coming in from above through the alcohol into the water, only these light rays can actually undergo total internal reflection. Rays coming from the water into the alcohol cannot undergo total internal reflection. Does that make sense?
Okay, I got it. Yeah, it makes sense. Thank you.
Yeah, so that's why, right, like the pictures I've shown you, when you go diving, you can see like a window of light right above you, but then darkness surrounding it. But when you're looking down at the water, it's all transparent because from our point of view, light coming from air to water always bends towards the normal, so you won't have a critical angle situation happening, which is why you can see into a slower medium everywhere. You can look anywhere in the swimming pool, wherever you stand, and you'll see below the swimming pool, you see below the water surface. But inside the water, looking up, you only see a small window above you. Oh yeah, this question. Okay, so this one's a bit of a challenge question. You are given two mediums and the interface between them where an incident light ray hits it. Some of the light reflects, some of the light refracts. And you don't know what the index of refraction is, you just know it's n and n prime. And you're told that the reflected ray is perpendicular to the refracted ray when a certain geometry is worked out. So yeah, from the beginning chapter, there's a lot of geometry that can be done with this mirror kind of setups, refraction and reflection, reflection and refraction. Gosh, get those two words always like, if you say them enough times, they just kind of slip up on them so easily. Anyways, so this question basically wants you to rely on the geometry of situation to figure out some trigonometric relationship between the indices of refraction of the two mediums. The best way to do this kind of question is to rely on drawings, right? You're told the reflected ray is perpendicular to the refracted ray. So, well, here's the reflected ray, here's the refracted ray. If they're perpendicular to each other, then if I measure the angle between them, I should get 90 degrees, right? So what else do we know? We know that the incident ray has some angle here, theta incident. By law of reflection, the angle of the reflected ray is the same as the incident ray. And by Snell's law, we know that n sine theta incident ray is equal to n prime sine of the let me move that, of the refracted ray. Right, so I'm gonna say, so at this point, Well, I wish I could zoom in on the picture. Actually do that? No. Okay, so we know that the angle between them is 90 degrees. So what you can then do is take advantage of the geometry, and you can actually derive then that the um, the cosine of the refracted ray is actually equal to the sine of the refracted ray. And wait, no, sorry, that's not true. You can actually show that the cosine of the incident ray is equal to the sine of the refracted ray. And then when you do that again, I'll leave that as an exercise, but there's a trick to the geometry that you can exploit to get this relationship here. And then if you just keep following that, then you have theta of the incident ray. I'm just going back to this formula here. It's equal to n prime cos theta of the incident ray. So n prime is equal to n sine theta of the incident ray over the cos of the incident ray as well. And that gives you n tan theta of the incident ray.
Sir?
Yeah.
How does the sine of the incident ray, well, like how does, like, how is n sine angle incident equal to n prime cos of incident? How, like, how
Oh
did you
yeah.
get that?
So let me zoom in to show that. So there's a bit of, yeah, it's better if I just draw it. Okay. You know what? I'm just gonna go to a whiteboard here. Okay, so we have let me draw the arrays. If you have an array like this, we have the normal line, which is, say, over here. And we have some kind of boundary box. They really not let you. You can't overlap stuff here. Okay, just setting up the normal here. Okay, so then we're going to have two rays coming out of this, one that's reflected, one that's refracted. The refracted ray, you don't know anything actually about the indices of refraction, but let's just say it's either going to refract away or towards the normal. We should know that the angle will be different. But we do know that it's parallel to the reflected ray. So we're going to draw the reflected ray. I'm sorry, it's perpendicular to the reflected ray. So they make a 90-degree angle. This is 90 degrees. Okay. So, so we know that this is the angle of reflection. This here is the angle of refraction. Let's call it below. And this here is the angle of incidence. So there's a few things you can do here. We know for a fact that 180 degrees must be equal to the angle of refraction plus the 90 degrees between the reflected ray and the refracted ray plus the angle of reflection. So does this make sense? Because I'm looking at what I'm looking at is this angle right here must be 180 degrees. So it must be that if I add every angle on this side, I should get 180 degrees. And if I shuffle some things around, I can then get a relationship between the reflected angle and the refracted angle, which is that I'm just going to do some quick algebra here. I'm going to bring 90 to the other side. This is the refracted angle plus the reflected angle. And now the relationship between the reflected angle and the refracted angle is that they're different by 90 degrees. So there's a 90-degree difference between the reflected and refracted angles. Now I'm going to take advantage of the law of reflection that tells me that the reflected angle is just the same as the incident angle. So then I can go plug this into here and get a relationship between the incident angle and the refracted angle. Now, something cool about this is the fact that the sine and cos functions are similar. They're just shifted by 90 degrees to each other. So I'm going to take the sine of both sides. Take the sine of the incident angle on one side and sine on the other side to get sine of the refracted angle minus 90 degrees. Here's a fun fact though. The sine function shifted by 90 degrees gives you the cos function. So cos x minus 90 degrees, or pi over 2 radians, gives you sine of x. And I wrote this backwards in there. Yeah, it's if you have sine x minus 90. Oh boy, where's my head today? Cos 90. Now, if you have a cos function and you shift that to the right by 90 degrees, you get sine, right? Because we look at the cos function. Look at the cos function on a graph. You just have to shift it by 90 degrees to the right to get the sine function. So if you take cos x minus 90, that gives you sine of x. Likewise, if you take the sine function and shift it to the left by 90 degrees, you get the cos function, because sine looks like this. So if you shift this by 90 degrees, you get cos. So sine x plus 90 gives you cos of x. Anyways, all this to say, because we have a minus 90 in this formula, then we should have been using the cos. If I take the cos of both sides, then it turns out that the cos of the incident angle is equal to the sine of the refracted angle. I'm just switching from a cos function to a sine function, since they're the same, just shifted by 90 degrees. So knowing this, I can now go back to the to Snell's law in the question, and I'm going to save this whiteboard as a picture. I'll show you later. I can now go knowing the relationship between the cos of the incident angle and the sine of the refracted angle, I'm going to go back to the question, do Snell's law. And so Snell's law will tell us that n sine theta I is equal to n prime sine theta refracted, but we know from whiteboard that sine of the refracted angle is equal to the cos reflected angle. So we now go ahead, plug everything in. And we get the there. So yeah, so like it kind of been warning for the few chapters we've done so far. You do want to get comfortable with sine and cos because they're showing up in every chapter, and they won't stop showing up until we get to modern physics. So we still got quite a way to go with our friends sine and cos. In other words, 2/3 of the course has formulas using trigonometry. I made sure not to have any in the midterm, but there's no way I can, write them off for these few chapters. It's a good time to get comfortable with them if you haven't already. Yeah, so I think that's all I wanted to do for this chapter, because this week we're supposed to be looking at the next chapter, talking about mirrors and lenses. So the main idea is that mirrors can be used to focus or diverge light depending on how they're shaped. And in the case of a concave mirror that's kind of bent away from you, they tend to focus light, and they'll create an image that's upside down. So nice drawing of it. Oh yeah, here. So I don't want to get too much into the algebra, but essentially what a concave mirror does is it'll reflect light upside down and create a image that's upside down. And if your object is far away from the mirror, then the image will be upside down, and it'll look like it's coming at the front of the mirror. However, though, we'll see that you can have an object that's really close to a concave mirror, and when that happens, the image will actually be in the bigger, it'll be magnified, and it'll seem like it's coming from inside the mirror, and it's called a virtual image. So in this case, the image was far away, so the object's far away, so the image is in front of the mirror. And every mirror, right, the assumption is that this concave mirror we're looking at is like a slice of a sphere. So there's some curvature to it and some radius associated with this curvature. The smaller the radius, the curvier the mirror is. So this mirror here is particularly curvy. And if you want to figure out where its radius is, you just kind of see if you can complete the sphere it was made of, right? So you can kind of picture this as being part of a bigger sphere, or in this case, it looks like a circle. It's kind of like a flat image. But then you can kind of see, right, that the radius is somewhere over here. And what mirrors have is a focal point where light converges, and it's defined in terms of where parallel light rays meet. So for example, in this drawing, so in this picture, parallel light rays are shot off from a distance and they all converge at a point right here. And this is then the focal point of the mirror. It turns out that the focal point of the mirror is actually always going to be half its curvature, so half its radius. So the radius of the mirror here, if you were to measure it like straight on the axis, will be right here, and halfway through is its focal point. Interestingly, if you place then an object some distance away from the mirror, you can actually figure out the distance where the image would be created if you know the focal length of the mirror. So in the case of the convex mirror, so if you take a concave mirror and you flip it, what it does is it'll make light rays coming from whatever's in front of the mirror. Light rays will kind of bounce off the convex mirror, and so they'll kind of fan out in many directions. But that makes the reflection on a convex mirror actually look smaller. So if you look at the backside of a spoon, you'll see your face, but you look a lot smaller. The backside of the spoon is a convex mirror. And for notation, when we talk about the object in front of the mirror, the distance from the object to the mirror is called P, and that's always going to be a positive value. So in the real physical world, distances are take positive sign, but in the mirror world, distances are negative. So the distance from the image form to the mirror is measured as the variable Q. And if the image is formed behind the mirror, Q is negative. If the image is formed in front of the mirror, the distance Q is positive. Images form where the reflected rays meet. So in the case of a convex mirror, the reflected rays are the red one here coming out towards the left and the blue one coming downwards to the left. So they don't actually merge, but they appear to have merged behind the mirror. And this creates a smaller image. So this is what happens when you look at the backside of the spoon. So here's an example of the convex mirror, which if you need to remember why they're called convex or concave, the concave one looks like it's caved away from you, it looks like a dent. The convex one is kind of popping out towards you like a bubble. So this one, you can it's almost flat, so its curvature is really, really big. The bigger the curvature the mirror has, the flatter it is. So this one's not that curved, so it has a very big curvature, but it is convex, so it is kind of, the bump is towards you. And as you can see in the ray diagram before it, it tells us that reflections of a convex mirror look smaller and appear to be behind the mirror. So right here, you see these trees and this house looking kind of small, kind of like they're coming behind the mirror. And that's what we expect from the convex. The images should be smaller than what they actually are. Oh yeah, what do you call them? The rear view mirrors in your car are convex. So they make cars in the rear view mirror look small, which sometimes gives you the impression that they're really far away because they look so small, but they're actually closer to you than you think. That's why there's that writing in rear view mirrors that say objects in the mirror may be closer than they appear. Yeah, so sign notation. Basically, in the real side, distances are positive. We usually draw the real side, the real world to be on the left side of the mirror, and the mirror world to be on the right side. So anytime the light approaches the mirror, reflected light bounces off towards the left. So for any surfaces, whether it's convex or concave or even flat, the mirror world is where you measure distances to be negative. So you can kind of think then as drawing like an x-axis through here, which I probably failed to do a straight line, right? Like it's kind of like an x-axis being drawn through here, but this side is positive x, and the other side is negative x. It's kind of flipped from what we're used to. So for a concave mirror, they can actually create inverted and upright images. If the object is far away from the focal point of a concave mirror, the image will be inverted and real. So you can see here, this flask is far away from the mirror that its reflection looks upside down. And you can't really tell in the picture, but the reflections, when you're far away from the focal point, will be smaller than the actual thing. But if you look at the bottom, what's happening in the bottom is that the flask is close enough to the mirror that it's actually a distance shorter than the focal length. So it's between the focus and the mirror itself. When that happens, when objects are that close, the image is actually magnified, so its reflection looks bigger. So like the flask here looks a lot bigger in its reflection. Also, the image is virtual. If you look at the rays, if you look at the rays of light just coming off the actual object, the actual flask, they bounce off, they reflect away. But in the way they do that is that it looks like they're all coming in from inside the mirror, and it ends up making the thing look larger. If you ever have like a little makeup case or like a shaving mirror, they're essentially concave mirrors, and when you bring them close to your face, right, they enlarge your face so you can see better, right? That's how they work. But if you move your face far away from a makeup mirror, you'll end up in this situation where everything looks inverted. You can actually do it with a spoon, by the way. If you have your face far away from a spoon, you'll have this image where your face is upside down. But if you move your face towards the spoon, you're really close. You'll need a big spoon to see this, but once your face gets really close to the spoon, everything will look upright and bigger. Oh yeah, and for convex mirrors, everything looks smaller. So reflections in the convex mirror, no matter what, are smaller than the actual object, and they appear to come from behind the mirror. So they're always going to be virtual images in the case of a convex mirror. Note that a virtual image is always upright. So the rays always seem to converge behind the mirror in such a way that the image is upright. Real images, however, are upside down. So anyway, so I'll talk about this in the lectures, but you can measure the position of an image when it passes through a prism based on the indices of refraction of the material outside the prism and the material of the prism. I'll talk about this later, but that takes you to figuring out lenses, where what lenses do is take advantage of refraction to focus or diverge light. So magnifying glasses, reading glasses all correct vision by making images appear bigger or smaller by, again, diverging or converging light. There's two kinds of lenses to talk about. There's the convex converging or convex lenses, which are called converging lenses, and what they do is they focus light. The other type of lens is the concave, or called the diverging lens, that spread light out. And you can actually figure out the focal points that these lenses have. Same way you do with mirrors, you shoot parallel rays towards the lens, and wherever they converge is a focal point. Convex mirrors have converging lenses have an actual focal point on the other side of the lens, but diverging lenses don't actually have a physical point where the light rays meet. The old fan outwards, but it looks like they were converging on the other side of the lens. And if you have an object on one side of the lens, you can figure out where the image is going to be if you know the position of the object and the focal length of the lens, whether that's a concave or convex one. There's some sign notations that are a bit different though. Like if you have your lens on the left side, on the left side of the lens, where the incident light is coming towards the actual lens, the object has a positive distance, but if the image is formed on this side, the distance is negative. And on the other side of the lens, if the distance is formed, if the image is formed on the other side of the lens, so when light crosses the lens, if it forms the image on the other side, the image would be measured as having a positive distance. And you can actually measure how big or small the image is going to be compared to the actual object as the ratio of the distances between each object, the object. So let me just state that. So the magnification of the image is based on the ratio of the image distance to the object distance. So if the image is farther away from the lens or the mirror than the object is, it'll mean that the image is being magnified. So that's how magnifying glasses work. You bring the object so close to the magnifying glass, which is a converging lens, but when it's so close to the magnifying glass, it'll actually magnify the image right in front of it. So that'll mean that the image distance is bigger than the object distance. The image actually is farther away from appears to be farther away from the lens than the actual page of the book it actually is. So for converging lenses, the way that they converge on object's light, as you can see it here, how the image is formed on the other side of the lens, and it's a real image when it crosses the lens, and it joins when the refracted light beams converge on the other side. We call that a real image. It's always inverted, and depending on where it is, it might be magnified or it might be shrunk. When you come closer to the focal point, the image magnifies. So if you place the object between the focal length of a lens and the lens itself, it'll produce a virtual image that is bigger than the object, and it'll be on the front side of the lens. So the distance q, the image distance, will be measured as negative. For the diverging mirror, no matter where you place the object, the image is always smaller and in front of the lens. So it only creates virtual images. They're always upright and it's smaller than the object. So a convex converging lens, these lenses here, in the previous slide, can be used as magnifying glasses, but these diverging lenses will have a minifying effect that will make the pages of the book you're reading look smaller. So again, much like converging mirrors, converging lenses can create real or virtual images, as you see in figure A and B. But in figure C, we have a diverging lens, which, like a diverging mirror, can only create virtual images. So just gonna get a bit of water. I'll be right back, and I'll get to some questions. Be right back. Okay. So a clown 2 meters tall looks at himself in a full-length mirror. Where must he stand? Where must he look if he wants to see his feet? So this question saying that there's a clown looking in a mirror. So let me draw that. And the mirror is, let's make this just like a, we're kind of seeing like a horizontal, like a snapshot of this, so the mirror looks flat from our point of view. Here's the mirror. It's kind of like a side view of the mirror, and what the clown sees then is, can I copy paste stuff? Man, can't. That sucks. Okay, but basically the clown sees the reflection in the mirror, and oh man, why does someone keep doing that weird thing? So here they see that they wish to see everything kind of bouncing back to them in their funny way. But the way that the light reflects is that to see his feet, right here, his funny clown shoes. To see his feet, that means that light is bouncing off his feet, and it's coming from his feet towards the mirror and kind of bounces back into his eyes. So the idea then is that at about a halfway point, right, the light from his feet appears to come from a point like halfway up the mirror, halfway up from his total height. So you can then think of them like a kind of like a drawing an axis here that splits the clown in half. And the total clown in height is 2 meters. The distance from the clown shoes to the halfway point where light appears to be coming from should be 1 meter. So if you look at the mirror, one distance, 1 meter up from the ground, you see your feet, assuming you're like 2 meters tall. But basically, if you look at the mirror, a distance from the ground equal to about half your height, that's where your feet are. Yeah. And if you see where your eyes are, well, there you just look straight on. You look head on to see your eyes, because light in a flat surface reaches the flat surface and reflects right back. If you want to see where your arms are, well, it's a bit of a different angle, but it's a similar idea. Anyways, the drawing here is showing you what I was talking about, but now that way you can look back at it for reference in the slides. So you see how the man's shoes appear to come from halfway through the virtual image, despite the fact that they're clearly on the ground, but the light that reaches you is halfway up the mirror anyways. So a concave mirror in this question, we're told it has a focal length of 20 centimeters, and you have to find the position of the resulting image. If you don't know where the object is, you just know that the image is inverted and 4 times smaller than the object. So to figure this out, we need to understand if the image is on in front or behind the mirror. And if you recall what I said, is that for mirrors, if I were to draw a mirror right now, just have the, whoa. Because you're told it's a concave mirror, the mirror is shaped like this, and we're assuming a light rays, right, will hit it from the left-hand side. But you're told by the question that the image itself is it's inverted. And that means that the image is real. Only real images are inverted. So a real image tells us then the fact that the distance, the image distance from the image to the mirror, it's measured as Q, is positive. Also, we are told that they were told something about the magnification of the object. We know that the image appears 4 times smaller than the object. We have a formula for magnification. And we're told that the object is 4 times smaller, so magnification must be 0.25. So then that gives us a relationship between the object distance and the image distance. And also, because the image is inverted, it should be negative 0.25. The negative sign on the magnification tells you whether you're inverted or not. Because we are inverted, we know we should have a negative sign here. So all in all, you get that Q is equal to 0.25p, or in terms of p, you have that the object distance is equal to 4 times the image distance. That means that if the object is over here, if the image is here, the object is 4 times farther away and is 4 times taller. So the object will be somewhere over here at a distance equal to 4q. And it should be 4 times the size of the image. So with that, we can use the lens equation to figure out the position of the image. So what we're looking for is the image position Q. And we have the lens formula that relates position image, object image, and the focal length. In this case, we have a relationship between P and Q, so we're going to take advantage of that. Then with some algebra, we can solve for Q, and you can show that Q is equal to 5f over 4, which we know the focal length, 20 centimeters, we get you 25 centimeters. So the object is 25 centimeters away from the focal length, and the image is 25 centimeters away from the mirror, and the object would be a meter away.
Sir?
Yeah.
Like, what's that t value at the that's pointing to, towards the dashed line?
Here?
Yeah.
Oh, sorry. That's an eye. That's like where the image is located.
Okay. Thank you.
And also, we can probably draw the image is at 25 centimeters from the mirror. The focal length is closer to the mirror at 20 centimeters. By the way, there's a few applets online you can use to work this out. If I go here, so this is for a convex mirror, which is exactly what we have. So I'll put a link to this in the chat. Why is it not letting me? Ah, here it is. So, okay, we can manipulate a few things here, but so here's a concave object, and we see that when the object is far away from the focus, the image will be in front of the focus, and it'll be inverted. And no matter how tall the object is, the image will be smaller. As you get closer to the focus, though, the image gets magnified and is now farther away from the focus than the object. So in our case, we had in this example, we kind of had an image being formed in front of the focus and the object was far away. So something like this set up here, but the image was 4 times as small, so the magnification would be a factor of 4. So the distance of the image, so the object should be 4 times away from the image. You can play around with it. You can also change the focus and see how that affects the image location. But it's cool that as you bring the object closer to the focal point, the image gets bigger. But then when the object passes the focal point, the image now becomes virtual. Anyhow. So this question is asking what a convex mirror, and it's the same question, but now it's a convex mirror. So what we have now is the focal length of -20. So here to show you another applet. What's the link in here? When you go from a convex mirror to from a concave mirror to a convex one, the focal length is on the other side, so you have to change your sign for the focal length from +20 to -20 in this case. So we had something like this going on in the first problem. We had a concave mirror far away from the focus, but now we have a convex mirror. So in this case, the convex mirror always creates a smaller image that's upright and looks to come from inside the mirror. So always creates a virtual image. The farther away you move the object, the closer the image is to the focus. If you bring the object closer to the mirror, the image gets closer to the mirror too, just on the other side. So in this case, you're told that the image is 4 times smaller than the object. So I wonder if I can actually make this work here. The image height, if I change the object height to say like 20. Okay, so it'd be something like this, where the image is 4 times smaller than the object. So you can kind of see what's going on where like the it's kind of looking like at the backside of the spoon where everything looks smaller but upright. And because the focal point is now behind the mirror, f is now negative in the lens formula. Okay, so yes, it's a convex mirror. You have this object here, and you know what the image is, might be a candle, and you expect the image to be over here, smaller. So knowing that the image is 4 times smaller, the magnification is equal to 0.25, it's equal to negative p over q. In this case, then q is equal to, let's say in terms of p, right? P is equal to, oh man, I got this, sorry, it's q over p. It's always in terms of the item, of the image. And then p is equal to negative 4 times q. And the reason why now it's negative is because the image is upright. So the magnification formula should give you a positive number because it's upright. So if we go back to the lens formula, 1 over q plus 1 over p is equal to 1 over f. F is now negative. The mirror has a negative focal length since it's virtual. So we plug in what we know. We have 1 over q minus 1 over 4q is equal to 1 over negative 20 centimeters. And if you do some algebra, what you end up getting is that q is equal to 3 divided by 4 times negative 20 centimeters. And that gives you negative 15 centimeters. So the image is a distance of 15 centimeters from the mirror. In a case of a convex mirror, the image is always within the space between the mirror and the focal point, no matter where the object is. So we go back to the drawing here. No matter where I move the object, you see that the image is either really close to the mirror or it's approaching the focal point, but the image doesn't move outside that space. When the object is close to 0, so is the image. When the object goes to infinity, the image goes to the focal point. Okay. So I got a question. Okay, someone just reminded me I didn't put the slides for chapter 35 up, so I'll put them up right away. Thank you for reminding me. So you're told about a concave mirror in this case. You know the focal length is 20 centimeters, and you want to know what the magnification is if you know the object distance. So being a concave mirror, right, that tells us that the focal length is real. It's in front of the mirror itself. I wonder if we can actually make this happen in the applet here. So the concave mirror, we know the focal length is 20 centimeters. So let's change the focus to be 20 centimeters. And we're told that the object is 100 centimeters away. So object distance. I would make this bigger. You can make the object bigger, but anyways, the main idea is that if the object, you keep pulling the object back, the image moves closer to the focal point. So our answer, we should expect the image distance to be somewhat close to the focal point, and it looks like the image will be real and upside down. And also it'll be smaller than the actual object. So you can see that the image looks smaller. So but all this information about the image being upside down and being smaller than the object, you'll find out through your formulas, because we use the lens equation here to find the image distance. Being a concave mirror, F will be positive, and in this case, Q will also be positive. But the equation will tell you that. So you have 1 over Q is equal to 1 over F minus 1 over P. Some quick algebra gives you that Q is equal to FP P minus F. And so that'll be equal to 20 times 100 centimeters squared divided by 100 minus 20 centimeters. So let me put brackets around that. This is going to give you the object distance. So you have 2000 divided by 80 should give you an object distance of 25 centimeters. Note that the answer is positive. That tells you that the object is, it tells you that the image is real, just as we expected from what we saw in the applet. And note that the focal length is 20 centimeters. So like we expected, the image is close to the focal length. But we need to find out the magnification of the object. That's a ratio of Q over P with a negative sign. So negative sign is there to account for the fact that real images are inverted. And so we have negative Q, which is negative 25 centimeters. P is 100 centimeters. So this ratio is a magnification of negative 1/4. That tells you the image is inverted and it's 4 times smaller than the object. So this question asks about a convex mirror with a focal length of -20. What is the object distance? So the image is just negative 10 centimeters. So this is a convex mirror, so it likes to disperse light. So here's the mirror, and the focal length, we're told it's -20, so here it is. The image distance is always between the mirror and the focal length. It's right here in this case. Because it's a convex mirror, images are always virtual, so we know for sure it's going to be behind the mirror, and it's going to be smaller than the actual object, that's for sure. I want to find out where the object is. We don't know this distance here, which is B. So we can use the lens formula since we know everything else. If you know P and Q, you can find F. If you know Q and F, you can find P. Just put this. So again, it's kind of like looking at the back of a spoon where everything looks smaller, or looking at a rear view mirror. So we have 1/P plus 1/Q is equal to 1/F. We want to find the object distance. So we're going to solve for P. That should be Q times F divided by Q minus F. And P will turn out to be a positive number. So everything's accounted for in this formula if we keep track of the signs. Q is negative. Should be 10 centimeters. So is F. Q minus F would be, careful with the signs. Q, again, is a virtual image. It's -20. It's minus F. Now remember that F is also negative, so it's actually 2 minuses. And what you end up getting then is the top part is positive. Is this right? Q minus F. Oh, no, I did not do this right. I plugged in 10 for Q and I plugged this in wrong. Sorry, the object distance is Q, which is 10 centimeters to the right of the mirror. It's this distance right here. This is Q. The focal length is 20 centimeters. It's over here. So we have 20 times 10 on top and 2 negative signs. We have 200 centimeters squared on top. And we have on the bottom, we have -10 plus 20 gives us 10 centimeters. So the object distance turns out to be 200/10, which is 20 centimeters. So the object, we know that this distance then is 20 centimeters to the mirror. So in this case, this question asks about a concave mirror, and the radius of curvature is given to us. So if we know the radius of curvature, we can actually find the focal length. So remember, like a concave mirror kind of looks like it's dented inwards. And we know that an object is placed 2 meters in front of the mirror. So there's an object somewhere over here at a distance of 2 meters. The radius of curvature is 1 meter. So if we were to measure the radius of this, you get 1 meter. The focal length is always half the radius. So F is the half the radius. So that would be half a meter. So for a concave lens, this far from the focal point. So for a concave mirror, where you have an object this far from the focal point, right? What do we expect about the image? Well, the image is probably going to be a real image. So kind of like you can see here. So you expect then the image to be inverted and to be smaller than the actual object. And given that we find everything but the image distance so far, we can then once again use the lens equation to get the location of the image. So once again, using the formula from before, P is equal to, sorry, Q. So now we're talking about the object. So rearranging the lens formula like we did, we got FP is equal to P minus F. The focal length is half the radius, and because it's a concave mirror, the focal length is measured as positive, so we have 0.5 for the focal length. The object distance is 2 meters divided by 2 meters P minus F being 0.5. So we get the distance of 1 over 1.5, and this should be meters. So this is about 0.67 meters. So that means then that the object is, the image is close to the focal point, and it's also going to be smaller than the actual object. If we look at the magnification, right, we get negative 0.67 meters divided by 2 meters. So that's about a third, so negative 1/3. So that means that the image, right, it's upside down because of the negative sign, and it's 3 times smaller than the mirror, than the object. Anyways, that's about all the time we have for today, since we're supposed to end at 3:30. Does anyone have any questions about these exercises we did? Nope. Okay, well, that's good. Because you're probably all pretty tired from the week, hey? Yeah. So yeah, for like equations wise, this chapter is really just doing stuff with the 2 types of mirrors and the 2 types of lenses. The stuff at the end of the chapter talks about different devices, and that's mostly conceptual. So that's worth understanding. You should be able to know how a telescope works compared to a microscope, right? Like what kind of mirrors are necessary to magnify a picture, and what kind of mirrors are necessary to magnify a picture that's really far away compared to one that's really close. So, right, it's a big difference between a telescope and a microscope. And beyond that, in about 2 weeks, you will have your second lab in the pendulum. Also, I'll hand out the 3rd assignment on the 24th. It'll be in this few chapters. For assignment 2, if you haven't done so already, please hand it in today. I want to get that graded soon. And otherwise, if you don't have any further questions, I'm going to call it an early day and let you go and enjoy the weekend. So wish you a good one.
You too, sir. Thank you.
No
Did
worries.
you have a good day too? Bye.
Yeah, well, have a good day. And yeah, I'll upload the chapter 35 slides right away.
Thank you.
Mhm.